Hello, everyone. Thank you for joining us today for this webinar on basic food analysis. I'm Trevor Morones from Control Point, and thanks for everyone from Hanna for joining us as well. It's top of the hour, so we're going to go ahead and get started. There's still a few people trickling in. If I could just get everybody to confirm that they can hear me in the chat, just give a Y for yes or type out yes, just to let me know you can hear me well. Awesome. Very good. All right. Michelle, you can go ahead to the next slide. So today's panel is Justin Mecys, Michelle Salisbury, Trevor Morones. I believe Justin might be coming in a little bit later, but he was a big contributor to this. Michelle, an absolute huge contributor to this, and then myself. We're going to get started and go into the topics now. Just a brief overview. So we'll be touching base on each of these topics. Be sure to ask your questions in the chat window for the question and answer session. Michelle and I will periodically stop and answer throughout if we see fit. And if we run short on time and your questions are not answered during the session, we will be sure to send a response directly. But let's keep the conversation going. Should there be more pressing questions, a conversation we need to have further, then please, by all means, keep it going. Here are some of the topics we're going to cover. Basic food analysis, like what is food analysis in terms of a little bit of history, definitions, and then we'll go in to talk about pathogen control, food safety, quality, our 6 HACCP principle, validation. Michelle will go into good lab practices, instruments, temperatures, lots of pH, and a little bit of moisture content. So today's poll is, what sector of the food industry are you in? Take a moment to answer the poll: manufacturing, wholesale, retail, food service, distribution, whatever sector you are in. Give it a few more seconds. We have just a few more voters. Looks like it's split pretty well. All right, here are the results. We have 14% in food service, 14 in retail, 57 in wholesale production, and 14 in distribution. We definitely expected most of the bulk being wholesale, but I'm glad that we have a little bit of everybody. All right. Go ahead to the next slide, Michelle.
Hi, sorry, are you seeing my screen, slide 5?
Yes, we see the screen. The poll is still up. So when we close the poll.
Sorry. Got it.
Awesome.
Sorry about that, guys.
No worries. Thank you, Michelle. So here's a great quote from Dr. Robert McGoran about basic food analysis. This is giving us the introductory to the rest of this webinar. And Dr. Robert McGoran has several publications. He's the department head at Oregon State. And his general research or focus is on flavor chemistry and trace volatile analysis, the effects of processing, packaging on flavor generation and deterioration, which we'll be getting into a little bit more later, and the identification of key aroma compounds in dairy and food products. So his quote here is, The growth and infrastructure of modern global food distribution system heavily relies on food analysis beyond simple characterization as a tool for new product development, quality control, regulatory enforcement, and problem solving. It's a really great quote. I see it, I use it quite often. So testing. When we're testing, what are we testing for? We're testing to be in compliance. We're testing because we're verifying that the contents on a label are indeed true. We're also testing for quality and consistency or nutrition, safety, or validation. In terms of labeling, in 1999, the Nutritional Labeling and Education Act, NLEA, was set in place so consumers can make informed choices about their diet. In order to claim the data was accurate, the data needed to be validated and verified. So in terms of quality and consistency, potato chip producers need to produce chips that are similar in color without being over-fried, what causes potato chips to be to appear darker or more brown. It's reducing sugars in potato chips. So the chips need to be analyzed to confirm the amount of reducing sugar. In terms of safety, we analyze our food to ensure that we are not promoting bacterial growth. Shortly, you will see a great chart about parameters in which bacteria thrive. And go ahead and move on to the next slide. We're going to begin to talk about composition. So composition of food largely determines safety and nutrition, physiochemical properties, quality attributes, and sensory characteristics. We have a chart coming up on the next slide that really gives us an idea of what composition is. It's a little bit difficult to see, but when we send out the slides later on, you'll be able to magnify it a little bit better. And this is from the New Household Discoveries Encyclopedia of Recipes and Processes from 1917. So we can see in this egg here, we have red is protein, yellow is fat, blue are carbohydrates, which the blue is very difficult to see, and it's more so in the cottage cheese than anything else. Brown is ash, and green is water. So on our next slide, we talk about further in depth about composition. We need to determine the property of interest to determine the analytical procedure. This is setting the platform for a lot of the details that Michelle will be going over soon. So we're looking for either specific atoms, specific molecules, types of molecules, or substances. When we talk about atoms, we're talking about hydrogen, oxygen, nitrogen, or carbon. For specific molecules, water, sucrose. For types of molecules, we're talking about fats, proteins, carbohydrates, fibers, minerals. And for substances, we're referring to milk, flour, nuts, and butter. So that gave us a basic understanding of what we are referring to when we say basic food analysis throughout this webinar. In terms of food safety, these are indeed true statistics. So out of 76 million cases of foodborne illness a year, 325,000 are hospitalizations and 5,000 deaths in 2010. But what we need to understand is, what is the process for these to be categorized, to be logged as foodborne illnesses? We need more than one person. We need 2 people minimum for it to be a foodborne illness. And the process it usually takes for those reports to be logged as data, it's about 7 steps. Because you get ill, how many of us have had food poisoning? You know, quite often. It happens frequently. But how often does it get reported? If it doesn't get reported, then your physician doesn't report it to the next phase of individuals. So now this is going to lead us into fat TOM. Food safety regulations work to control fat TOM. So when we're controlling fat TOM, we're controlling microbiological spoilage. In particular, dairy products present an especially favorable environment for microbial growth. But not only dairy products, we have produce, we have looks like cured ham in there, there's cheese, which is part of dairy. We have bread. We have an RTE pizza. Looks like that pizza's been in there for quite some time. So microorganisms favor food products due to their high moisture content and nutrient content. Even food that is free from microbes can readily spoil if the conditions are right. When we are controlling microbial growth, we're referring to two different types of environments, two different types of factors, intrinsic and extrinsic. For extrinsic, we're talking about environmental controls, temperature, humidity, microbial environment. Microbial growth is controlled through extrinsic and intrinsic factors, and cleaning serves to eliminate external microbial contamination of food. In terms of intrinsic, relates to the properties of the food. Water activity, moisture content, pH, acidity, or antimicrobials added are naturally occurring. Here's our beloved acronym. This acronym is great because not only do we see it in terms of food service, but it's also used throughout wholesale as well. So, FATCOM, food, acidity, time, temperature, oxygen, and moisture. Food, availability of nutrients for microbial growth. Acidity, microbes thrive in slightly acidic to neutral conditions, which is 4.7 to 7.5. You'll see a great chart later on. In time, food should be held at temperatures either 5 to 60 degrees Celsius for a minimum amount of time, which is less than 4 hours. And temperatures, since microbes grow optimally between 5 and 60 degrees Celsius, food should be stored below these temperatures. In terms of Fahrenheit, we're talking about 41 degrees to 135 Fahrenheit. Oxygen. Many microbes rely on oxygen to grow. They're aerobic, so oxygen is minimalized in packaging. That's ROP or MAP packaging, which is a modified atmosphere packaging where the package is being flushed. In terms of moisture, living things require water to grow, so the more available water leads to higher perishability. This is a great chart. We use this in validation for processing salumi, and it works for so many different things. We have 9 major pathogens here: Salmonella, Clostridium botulinum, Clostridium perfringens, Staphylococcus aureus, Campylobacter jejuni, Listeria, E. coli, Shigella, and Bacillus. Notice that under the column minimum water activity, 0.85 is bold. Significant growth of Staphylococcus aureus occurs at 15.6 degrees Celsius and higher, and after fermentation of the sausages should be dried below this temperature. Fermentation tables are based on this fact. So we see that how some of these microbes act differently than others. Listeria is definitely a big one because it survives in freezing temperatures. But staph is definitely one of our bigger pathogens of concern in salumi production. All right, federal regulations. Who are these regulations? Well, they're the FDA and the USDA. Well, in terms of FDA, we refer to 21 CFR, and in terms of USDA, we refer to 9 CFR. Coded index of all the rules and regulations published in the Federal Registry by branches of the government. CFR is composed of 50 titles, but separated by subject. The majority of the CFR titles do not concern food and beverage production. For example, Title 32 is national defense. In the U.S., food and beverages are regulated by 2 separate but totally important groups, the groups we already mentioned. And division is way more complicated than this actually is. It's getting quite muddy, and obviously we're seeing a shakeup with FSMA, the Food Safety Modernization Act, coming in, and the final rules being published. So plants have a reducing window of opportunity to make sure they're in compliance with those things. And then we're seeing the USDA shake things up as well. All right, let's take a step back. What is HACCP? HACCP is Hazard Analysis Critical Control Points. And there's 7 principles that encompass HACCP. But HACCP itself is a food safety management system. It's not as complex as the regulatory authority generally likes to make it. It definitely requires a lot of training and reading to really understanding it and practicing. So principle 1, we identify our hazards. We assess the situation as a whole. There's a little bit, it's not as vague as this particular conversation, but if you're interested in some HACCP training, we can talk about that on another time. So once we've identified our hazards, we identify our critical control points. Where do we need to control these hazards? Where are they going to be most likely to be introduced into our system? Once we've identified what those CCPs are, we establish our critical limits. Remember, these limits are referred to, we talk about them in general as a range, but it needs to be specified in your plan as one particular number, either a minimum or a maximum. For instance, if we're talking about temperature, we don't want to go above 41 degrees Fahrenheit when we're processing meat, poultry, and other foods. 4, I'll go back from Michelle, thank you. Implementing continuous monitoring. So after we've established the critical limits, we need to make sure we have monitoring procedures. After our monitoring procedures, we need to implement corrective actions. Should we deviate from the CCP? Once we've implemented those corrective actions, we have to prove that the plan is working accordingly. This is validation and verification. We'll get further with that in a second. And then documentation. Always document everything. And don't falsify your documents. You forget to do something that deserves a corrective action, explain why, and then try to prevent it further on. Always, always document everything. All right, now we can go. So shelf life studies. Shelf life studies, there are 2 particular ones. We're talking about accelerated or real time. According to the Institute of Food Technologists, IFT, and the National Advisory Committee on Microbiological Criteria for Foods, you'll see this acronym a lot, NACMCF, shelf life is the amount of time that a product is considered acceptable for consumption when stored at the appropriate storage conditions. So when determining if a food product is acceptable for consumption, several factors are taken into consideration. This includes organoleptical properties, taste, texture, odor, appearance, and microbial spoilage, chemical changes. In terms of real time, we're conducting under normal conditions of the product, and it's carried out greater than expected shelf life of the product. It's periodically evaluated to determine the point of deterioration. In terms of accelerated, we're predicting the shelf life of the product without running full trial, and generally performed for products that have longer shelf life. And predictive mathematical models to project the spoilage. And if you'd like that formula, I'll be sure to share that with you. Go ahead, Michelle. So I wanted to talk about shelf life studies before validation because I wanted you to understand that when we validate something, when we're running a shelf life study, we're validating something. We're validating our shelf life. We're saying that this is going to be good for 7 days, 14 days, 21 days, whatever that may be, and our validation is the proving grounds for this. So validation is process of the determination that the HACCP system is designed can adequately control identified hazards to produce safe, unadulterated products. So our HACCP system is defined as the plan in operation, including the plan itself. And our plan is defined as the hazard analysis, any supporting documentation, prerequisite programs, and supporting decisions in the analysis, and all the HACCP records. Validation is such a key component. When I was saying that we're going to get into the USDA shaking things up a little bit this year, one of the things that they're looking at is the initial plant validation. They're saying that a lot of plants aren't following their initial validation, and though they put together a study, they never really carried out the entire study. Generally, it's 90 days. So the Federal Register notice announced that establishments will have until January 4th, 2016, which is passed, and April 4th, 2016, which is already passed, to gather any data they may no longer have. At that time, the FSIS will issue necessary instructions to field personnel for them to verify the establishment meet all validation requirements. Under 9 CFR 417.4A1, establishments are required to assemble 2 types of supporting documentation to demonstrate the HACCP system has been validated, and that's scientific or technical support and the initial in-plant validation study, which is the actual execution of it. Initial validation encompasses activities designed to determine whether the entire HACCP system is functioning as intended. That's the importance of validation. Okay. At this point, Michelle is about to take over for us. I appreciate you guys listening, and please be sure to go ahead and put your questions in so that we can either answer them as we go through the slides or at the end in the Q&A session. Michelle, thank you very much, and the floor is yours.
Hi guys, sorry about my twitchy slide progression, Trevor. I appreciate it, and thank you for the information. So for those of you guys who know me, my name is Michelle Salisbury. I'm the Applications Manager here at Hanna Instruments USA. What we're going to be talking about today is food testing. So Trevor just gave us all the regulatory reasons and quality reasons why we might want to do food testing in-house. So we're going to get a little bit more into the details about the most common parameters that people might move for in-house testing, the different methods available for those parameters such as temperature, pH, acidity, sugar, salt, and moisture, and just some of the overall benefits about in-house testing. So there's 3 main reasons in which you might test in-house: for food safety, for food labeling, or for food quality and consistency. So Trevor covered the first 2 in pretty good depth, but I want to just talk for a moment about the third one. So if you're measuring for food safety or food quality, or for food labeling rather, typically you have to do this for some kind of reporting, whether it's to the FDA, whether it's to an internal quality agency. The food quality and consistency guidelines are typically self-guided, and this is more to ensure consistency between batches over time, as well as overall quality that's not related to safety. So the first parameter we're going to talk about is temperature. So temperature is the most widely measured parameter in the entire world. When we talk about measuring temperature in food and we look at a graph like this, it becomes obvious why it's especially important in food safety. So the growth of bacteria at room temperature, you can see, is exponential, and after only 5 hours you can have a bacteria count of over 3 million from just a starting population of 100 cells. So if any of those are harmful bacteria, it's easy to understand why food safety concerns and why outbreaks and illnesses can occur. So there's a couple different types of thermometers that you can use to measure temperature. And what's going to determine which of these technologies is the best fit for your application is going to be what range you need to be in, what accuracy you need, what the response time is that you need, and whether or not there are specific probes that you need as well. So just some examples of what some of these thermometers look like. Infrared thermometers obviously do not contact food. These are, the two in the middle are some portable thermometers that are capable of being certified by the manufacturer, so they have like a traceable calibration. And then there's also pocket types of meters available as well. This is an example of some different probe variations, so surface probes, air and gas probes, pipe clamp probes. And then here's just a quick chart which compares the different technologies and what their limitations and what their benefits are, so what their range is, accuracy, and response. So with any type of measurement that we're performing in-house, the first thing we want to make sure is that we have the right instruments for that measurement. So if you're going to be measuring in an oven, probably a thermistor would not be a good fit for you with a top range of 220 degrees Celsius. If you're going to be measuring your food that you're boiling, probably an infrared thermometer with a limited accuracy wouldn't be a great fit for you. Things like this. All right, we're going to move on, and we're going to have a pretty heavy focus here on pH because it's one of the most commonly measured parameters in food laboratories. The pH is actually the second most commonly measured parameter worldwide, only to temperature. The pH is a measurement of the hydrogen ion. So what does that mean? That's the ion that determines whether something is an acid or whether something is a base. So this is based on pure water, which dissociates to hydrogen ions, which contribute to something being an acid, and hydroxide ions, which contribute to something being basic. The pH scale ranges from 0 to 14, and we can see some normal household objects and where they fall along this range. You'll see that most things in the food and beverage industry tend to be on the acidic side, so below pH 7. pH is really important in terms of complying with the federal regulation CFR 21. We saw a chart that Trevor shared earlier where it showed different bacteria, their optimum pH ranges and optimum temperature ranges for growth. And we found, or scientists have found, that bacterial growth is inhibited below pH 4.6. So this is kind of a magic number in food when we're thinking about shelf life and whether or not something needs to be refrigerated or can be considered shelf stable. So in order to comply with this regulation, typically foods need to be either inherently below 4.6 or acidified with some food-grade acids to drop below this range to prevent microbial growth. Acidity also affects the way things taste. So this is a great chart. Again, it's the pH scale, but it shows where a bunch of different foods fall on that scale, and we can kind of correlate that flavor profile to that pH. So things that are more sour, like lemons and limes, are on the acidic side, or things that taste more neutral, like cheese and milk, are closer to a neutral pH. So measuring the pH can also help us maintain a consistent flavor profile from batch to batch. So there's a few different methods to measure pH, but we're going to focus on the potentiometric method, which is this method right here, a meter and an electrode. So when we're classifying foods as either acid foods, low acid foods, or acidified foods, as part of CFR 21, the regulation dictates which of those methods we can use to measure the pH in order to comply with CFR 21 by the FDA. If the finished pH of the food is less than 4.0, you can use any method for measuring pH, a colorimetric method. But if you're in that critical range, like right on the line of whether or not that food is shelf stable, which the regulation defines as between 4.0 and 4.6, that potentiometric method must be used. So we're going to take another quick poll, which is, are you guys measuring pH in-house? And if so, how are you doing it? So far, we don't have any questions, but if you guys do, you can type them in now. We can answer them while you're taking this poll. Perfect. So, looking at our results, we see that 29% of our audience is measuring pH in-house with a meter and electrode, where 71% are not currently measuring pH in-house at this time. So we're going to go ahead and talk about the best measurement practices for measuring pH, as well as, if you're considering bringing it in-house, how to, again, determine that you have the best instrument and the best set of tools for that job. So, not all pH electrodes are created equal. This is an important point that I want to make today. There's a bunch of different characteristics of a pH electrode that can be customizable for your testing needs. The first and one of the more important ones I want to talk about right now is the bulb shape of your electrode. So, most standard electrodes come with a spherical tip. This has a great amount of surface area. It has a great response time in aqueous liquids. So if you're using a liquid-based sample, this is probably a good fit for you. However, a lot of foods are not liquids. They're solids, or they're semi-solids, or they're viscous, or they're even solids. So an alternative tip shape might be better. A conical tip lets us penetrate our sample, such as a cheese or a yogurt sample. A flat tip allows us to take a surface pH of things like leather or other surfaces. So customizing this tip can give you a little bit more flexibility in your measurement. The electrode body type is also customizable. So a lot of HACCP plans will try to dissuade having hazardous materials on the production floor, such as glass. So electrode bodies can also be made of plastic, titanium, or stainless steel. There's also a whole variety of glass types. So that main component of our pH electrode, which is helping us get that measurement, is that pH sensing glass. Now, standard pH glass works in most applications, but if you're using an electrode at a very high temperature, that glass will break down pretty quickly and your electrode lifespan can be pretty short. So there's actually a high temperature glass formulation that offers a longer electrode life in those situations. If you're working in a refrigerated sample, that standard glass might be slow to respond and slow to give you a stable measurement. Using an electrode with a low temperature glass formulation will give you faster response time and better stability in those cold samples. Another extremely important electrode characteristic in the food industry is the type of reference junction. So, pH electrodes work with a sensing glass on the outside and a reference potential which is generated on the inside of the electrode. There is a junction or salt bridge that connects those two potentials. For most standard electrodes, again, this is just a tiny single ceramic frit. If you have a liquid sample that doesn't have any solids, such as pure water, a single ceramic junction might be okay. However, if you're working in samples that have pulp, like an orange juice, or have some microproteins or fats, this ceramic plug can get clogged. If that junction becomes clogged, then we can't connect our circuit and our electrode stops working. So some of these high flow rate junctions, such as 3 ceramic junctions, a Teflon junction, open, or a sleeve junction, give us a higher flow rate, better surface area, and better electrode lifespan than that single ceramic junction. These open junctions designs actually allow us to insert a pH probe into a solid or semi-solid sample and take a measurement without having to make a slurry. So when we're talking about food and we're comparing, which type of junction would work best, for the most part, these 3 on the right are PTFE, open, and sleeve junctions, offer a little bit more flexibility and better performance than ceramic junctions. So Hanna makes a whole line of Foodcare electrodes for a bunch of different types of samples. So from everything from liquid samples to semi-solids to solids. So this picture shows our electrode with a sleeve junction in an orange juice sample with some pulp, our meat electrode taking a direct measurement of meat, again, no slurry required, or our yogurt electrode taking measurement in yogurt. So again, when you're looking to bring this type of measurement in-house, you want to make sure that the tool is the best fit for what you're doing specifically. The last thing that affects this could be the type of connection that your electrode has. So a BNC is a standard electrode connection. These require a separate temperature probe in order to get that temperature compensation, but they're flexible, meaning that you can use many different electrodes on 1 meter with the standard connection, switching back and forth. A DIN connection is a proprietary electrode connection, so it might be that a certain meter only works with this one kind of electrode if it's a DIN connector. But they do offer some advantages, such as they often have a built-in temperature sensor, meaning you don't need that separate probe, or they might be amplified for faster response time and better stability. The last type of connection we want to talk about is Bluetooth. This is a proprietary wireless electrode connection that also offers a built-in temperature sensor. So you can wirelessly connect to a meter or an application. In terms of meters, you can go with a benchtop meter if you're working in a lab, what we call a hybrid meter, so it can work as a bench or it has a portable mode as well, such as our Edge or even an iPad or an iPhone. And then there's also very rugged portable meters that are more built for the production floor. So you have the right electrode for your application. You have the right meter for your application. Now what? We're going to talk about calibration. So pH electrodes are all designed based on something called the Nernst equation, which is a scientific equation dictating how, theoretically, a pH electrode works. However, we know that not all pH electrodes behave exactly this way. If all pH electrodes behaved exactly in accordance with the Nernst equation, we would never have to calibrate. And how nice would that life be for us? Unfortunately, we're not there. So pH electrodes differ from this theoretical behavior due to how old the electrode is, the manufacturing process, and what that electrode condition is, if it's clean, if it has some coating on the bulb, something like that. So calibration tries to compensate for these differences. So we can see our blue line is a real electrode, and that red line is a theoretical electrode. So when we calibrate, it changes the internal algorithm of the meter from this theoretical line to the line that your meter is actually operating on. So that allows us to get those accurate results. When we're calibrating, we want to make sure that we're bracketing our expected pH range. We always want to calibrate at pH 7 and at least one other point, and our calibration point should be more than 1 pH unit apart. So just some examples. A lemon is pH 2.0. Which points would we want to calibrate to? The recommendation would be 7.0 as always, and then 1.68, and since those 2 points are pretty far apart, if you have the option to calibrate to 3 points, a calibration point of 4.0 would also be recommended, and that will give us 3 points along that range to get maximum accuracy around our expected value. Milk has a pH of about 6.5, so calibration points at 4.0 and 7.01 are recommended. For some reason, my picture on the end here isn't showing up, but there is a cute little box of Alka-Seltzer, which has a pH of 12.0. So we would recommend calibration points at 7.0 and 12.45 to bracket that range. And if you have the option to calibrate to a third point, we'd also recommend a calibration point at 10.0. So calibrating can seem kind of daunting, especially if you're not currently measuring pH in-house. There's certain meters, such as Hanna, that offer some diagnostics that kind of take the guesswork out of calibration. So Hanna's program is called CalCheck. It's an exclusive feature that provides indicators to potential problems during the calibration process. So we know that our electrode might not be behaving perfectly, but if from Monday to Tuesday we see a 20 millivolt shift in the electrode offset, that big of a shift isn't typical for one day's difference. So our CalCheck will say there's been a big change, perhaps the electrode needs to be clean, or perhaps the buffer is contaminated. After calibration, it will give you a readout on the condition that your electrode is behaving based on that calibration. So if your condition is good, you can be confident that your readings that you take with that calibration will also be good. After calibration, you want to make sure you're storing your electrode properly. So the storage solution, it's optimized for the ionic strength, and you give you that optimal hydration layer on your pH sensing glass. If you don't have storage solution available, pH 4.0 or 7.0 buffer are pretty good substitutes, but we never want to store the electrode in alkaline buffers or in deionized water. We also want to clean periodically, and in order for this to be effective, you want to make sure you're using the best cleaning solution for your electrode. So here's a list of some of the cleaning solutions that Hanna has available. All right. We're going to move on, and we're going to talk about acidity and pH. So acidity and pH are related, but they're also exclusive. pH tells us whether something is an acid or whether something is a base. Acidity is going to let us know what the concentration is of that acid in the sample. And we're going to determine that by determining how much base it takes to neutralize it. So this is a procedure called titration. So in foods, typically both the strength and the quantity of the acid, so both pH and acidity, are important. So typically both are monitored together. So for those of you guys that might not be familiar with titration, we're going to quickly go over what a titration is. So titration is determining a concentration of an analyte. So in this case, our acid concentration for acidity. We do that by reacting it with our titrant. This is a substance that's a known concentration. We're going to measure the volume. So we know exactly how much volume and exactly what strength our titrant was. And we're going to titrate to either an equivalence point or an endpoint, depending on our method. So once we reach this endpoint, we can quantify how much titrant we use, which can then be used to calculate how much analyte was present. So all acidity determinations require a base as a titrant. They're carried out to a neutralization point. And it's really important to note that this can be used to determine the total amount of titratable acidity, but we can use it to differentiate different acids, as that base will neutralize all acids present in the sample. So for orange juice, we can measure that total acidity. We'll probably express the results as citric acid, since the majority of the acidity is from citric acid. But we can't use titration to determine how much malic acid and tartaric acid and citric acid are present. All we can do is do it one group number. So when we're titrating this, we can do a manual titration to a color indicator. So the most common for acidity titrations is phenolphthalein, so it turns a pale pink color. We can also do a manual titration to a fixed endpoint, or we can do an automatic titration to a fixed endpoint or equivalence point. So we can see here that if we plotted out how the pH changes as we titrate, we can see where that color indicator lines up. All right, we have one more poll that we're going to do today, and I see we have a couple questions that we can answer while we're doing it. So Jason Pepper asked, for a BNC connector, do you always need a separate temperature probe? So for the most part, Jason, the answer is yes. Some probes will have a temperature probe housed in the same body, but it will have a separate connector on the meter. The BNC connector doesn't facilitate the electronics needed to measure both temperature and pH. You either need like a separate pin or a completely separate plug-in for that probe. That's the advantage of DIN connectors, which are a little bit more sophisticated, but also a little bit more exclusive in terms of flexibility between probe and meter. So great, looking at our results from those of you guys that answered for us today, we have 50% of us that are doing titrations automatically and 50% that aren't doing any titration. So we have a little bit of a discrepancy here. We have a bunch of you guys who are doing them automatically already, which is great, and a couple of you guys who aren't doing it, so hopefully we can make you some converts. So I quickly want to go through the advantages between manual and automatic titration. So if you're not already performing titrations in-house and you're considering it, you're probably wondering if you should jump into an automatic titration or if a manual titration will suit your needs. The manual titrations require manual dosing with a burette, and that person actually has to stop dosing when that endpoint is reached. So whether it's a pH of 8.3 is shown on the meter or when that pink color appears. So these can be a little bit subjective, and therefore they have limited accuracy. And not all titrations are super feasible to do manually as well. There are these middle-of-the-road, we'll call them automatic titrators, such as our mini titrator. They do one thing. They're really easy to use. They're also pretty inexpensive. And then we also have fully flexible automated systems. So this would be for a user who wants to bring more than one parameter into their house, such as salt, such as acidity, such as reducing sugars, etc. So we've talked about temperature, we've talked about pH, and we've talked about acidity. We're going to talk briefly about sugar now. So depending on what kind of food that you're making, sugar can be an extremely important parameter. The most common way to measure sugar in-house is with refractometry. Now, the important thing to know about refractometry is it's not specific. This allows us to measure the total refraction in our sample, which might be from sugar, it might be from sugar and other components in your food, and it will give us the results in our choice of units. So how does a refractometer work? As light passes through one medium to another, the speed of that light changes, which causes the light to bend. So if we have light passing through a glass full of air, it's not hitting any resistance, that light isn't changing. We don't see any bending, that straw appears perfectly straight. If we have light passing through a glass of water, as the light goes from air to water, the speed of that light changes, so we can see the straw appear slightly bent. When we add something to that water, such as sugar or salt, the light reflects off those particles, or refracts, and we can see the bend in that straw is even more significant. So how do we quantify that? Lights pass through a solution, and we can see that there's a reflection or a shadow point based on how much stuff is dissolved in that sample. We can quantify this using a manual refractometer, where we would look through and we would manually line up that shadow line to our concentration, or with a digital refractometer, which will determine that concentration for us using an internal algorithm and give us that digital readout. Refractometers are really great because they're super easy to use. You turn them on, zero them, add your sample, and you have a reading, and that whole process takes under a minute. So there's a whole line of refractometers you can purchase, which will give you results in different units. It's important to remember that all of these units are measuring the same thing, total refraction of light. And then using an internal calculation, they're correcting the temperature, they're expressing the result as that parameter. So the 96801, 96802, 96803 are all reading the same result, but expressing it as different ways. So refractometers are great if you have a solution that's only two things, sugar and water. So perhaps if you're making a simple syrup. If you have many components in there, then refractometers can be a great qualitative measurement about the composition of your sample. All right, we're going to move on to salt. The salt is a really big focus in the food industry these days with all the health concerns and buzzwords going around about low sodium and reduced sodium foods. So it's important to keep in mind that with regards to food, salt and sodium are not necessarily synonymous. Although most of our sodium in food is derived from NaCl, there are other potential sources, including baking soda or MSG or other preservatives. So for salt, most methods of analysis require liquid samples, so solid foods might require additional preparation. So depending on what kind of method you're trying to comply with, you may need to prepare a slurry, which is basically food mixed with deionized water in which the salt is extracted. Or you might need to do a chemical extraction of that salt using something called a digestion. This typically will require a strong acid or a strong reducing agent. And this allows us to get salt that might be bound in particles that otherwise wouldn't be extracted in water. So there's a bunch of different methods that are available to measure salt. Your method selection is going to depend on what your accuracy requirements are, what your sample matrix and sample preparation requirements are, how easy does it need to be, what's your industry type and your budgetary concern, and what other interferences do you have present. So we've broken them up into two main groups. The first we'll call simple methods, which again are great for binary solutions, such as a brine that's salt and water, or they're a great qualitative indicator of salt content, and these are conductivity or refractometry, and then analytical methods. So this would typically be what you need to use if you want to comply with a standard method, if you want to use this for regulatory reporting. And these methods are going to be titration or an ion selective electrode. We're going to focus mostly today on refractometry and titration for salt measurement. So for titration, we're doing actually a measurement of chloride, and from there we're inferring sodium chloride. So we take our sample, we extract all the salt into a liquid matrix, and we add silver nitrate. This reacts with chloride to form silver chloride, and we are able to use that titrator to determine where that exact equivalence point is. This is the most common method in analysis of standard methods, including AOAC, the International Dairy Federation, and ISO. These can be performed manually to a color indicator, or automatically to an equivalence point as shown on our graph here. So we've already talked about refractometry in terms of sugar. So here's a quick table which shows the advantages and disadvantages of each of these methods. So again, if you're looking for a quick check, perhaps you're trying to make sure that there's enough seasoning on your peanuts, refractometry might be a great fit for you. If you're looking to be really quantitative about that salt content in your food, then titration is going to be a better investment. The last thing we're going to talk about today is moisture in food. So water is, of course, present at several stages of food production, right? And whether or not this water ends up in the finished product has huge implications. So it's important to know what kind of water that the customer wants to measure when we're talking about this. We may be wanting to measure total water, free water, or bound water. So depending on the product, these three types of water might differ, or they might be the same. One measurement technique that is used is called loss on drying. This basically takes your sample, you weigh it, you put it in an oven, typically for an extended period of time, 24 to 48 hours. The assumption is that that water is evaporated under that higher temperature, and then you weigh the sample again. That loss in mass is assumed to be water content. This is pretty good as long as your sample doesn't contain a lot of volatile components. If you have a lot of volatile components, these will also be lost in the oven and cause an interference in your reading. So one example would be apples, which have over 300 different kinds of volatile components in them. So if you're really trying to quantify water, loss on drying might not be the best method. Probably the most common analytical method for water in food is water activity. So water activity is pretty much a measurement of how much free water is in there. So free water we define as water that's available for microbes and other organisms to use. So again, Trevor talked a little bit earlier with his chart, and he talked about, I think it was botulism that thrives at a water activity over 0.85. So that's that free water measurement. Sorry, staph infection, not botulism. But 0.85 is, again, a pretty critical point when we look across the board in terms of microbial growth. So here's a quick chart which shows our ranges of water activity and the potential growth for microorganisms. So we can see we start to have some growth at water activity above 0.6, and those really harmful bacteria that we're worried about really start to take off when we get above 0.9. I believe for CFR 21, if you have to comply with that regulation and report on that, your food has to have a water quality above 0.85. If your water activity is less than that, then you're exempt from that regulation. The last method for measuring moisture is Karl Fischer titration. This is a method that's most commonly used for measurement of total water. It's a chemical method, which means that it's specific to water. So unlike loss of drying, which will measure water and other volatile components, Karl Fischer only measures water. And it's also commonly used in industries where water activity just isn't feasible. So one great example of that would be edible oils. Karl Fischer is the way to go. So again, a quick comparison of methods. So loss on drying will measure all volatiles, including water. The time for analysis is usually overnight. It's inexpensive, but it's time-consuming. It's a slow turnaround time. Water activity, it's free water. It only takes several minutes. It's fast, but it only measures free water. So you have to know which of those measurements is the most important for you. And then Karl Fischer will measure that total moisture, but it does require some non-aqueous solvents, which are not, typically the most friendly chemicals, and some lab technique to get those results. So, I know that was a lot of information in a short amount of time, but let's do some conclusions real quick. So, if you're thinking about bringing testing in-house, this can give you faster turnaround time on your testing results. So if you're currently sending tests out to a lab and you're waiting to hear back from that lab before you can package your food to make sure that it's meeting those regulatory compliance, this will allow you to make that determination faster and on your timeline. It's less money per test. So if you're sending pH measurements out in the lab, that can cost up to $20 a test to do at a third-party lab. At that price, you're probably not doing it that often. So bringing this in-house can allow you to get more measurements for less cost. This can help you improve compliance. So if you're able to take measurements at each step in the process instead of waiting to test the final product, if there's something that's out of specification on that project, you can either stop that production early and save time, or correct that mistake and salvage that product. So I know Jason had just sent me a note about a customer who was actually making wine, and they were not doing any testing in-house. They sent their finished product out, and they found that their volatile acidity was outside of the specification. So they had to pay a pretty significant amount of money to have that volatile acidity removed with an advanced filtration process. Testing in-house as you're making that wine allows you to make those corrections earlier, which will save you money at that point too. And then, of course, this will allow you to increase the food quality and consistency of your brand and just increase your customer satisfaction accordingly. So now we're going to go ahead and we're going to do our question and answer session. So I see we have a question here about where we can purchase calibration liquids, and if the liquid expires, what should be done with it. So that's a really great question. Calibration liquids can be purchased a number of places, including from the manufacturer of the instruments, hobby shops such as aquarium or hydroponic shops. Typically, we recommend that if these instruments are open for more than 6 months, they should be disposed of, and they can be disposed of in the sink for the most part if we're talking about pH calibration. And it's important to remember that your calibration of your instrument defines how accurate your measurement is. So if your calibration solutions are expired, you have the potential to be getting an inaccurate calibration, which means that your measurements could be inaccurate. So obviously that's not where we want to be. Do we have any other questions today about any of the information we just went over for myself or Trevor? All right, we just have a second question on where calibration liquids should be stored. So it's really important. We don't want to calibrate. We don't want to contaminate our calibration solutions. So we recommend pouring some solution out to a beaker, and once that liquid has been used, not pouring it back into the bottle. You don't necessarily need to use fresh liquid every time, but we'd recommend sealing that calibration beaker with parafilm or saran wrap, something like that, and using fresh buffer at least weekly, if not more frequently. Okay, perfect. If we don't have any other questions, we just want to thank you guys for coming. If anybody is interested in talking more about some of the technologies that we've gone over today, please reach out to myself or any of our very competent sales staff here at Hanna Instruments. We are offering a coupon code for those looking to invest in some new instrumentation or some buffers or consumables. So this code is HACCP. It can be used at our website or by calling in and speaking with one of our sales reps through May 15, 2016. We have one more question about how specific cleaning solutions should be before I give this back to Trevor. If your cleaning solution isn't dissolving or removing what your sample matrix is, then there's really no point in doing it. So if you're working with something that is really fatty and has a lot of oils, typically a basic cleaning solution will dissolve those fats more appropriately. So think about when you wash your laundry. We use this very specific laundry formulation because it's made to remove dirt and grease. If we used some, dish soap in our laundry, that wouldn't effectively clean it. So it's the same kind of parallel when we're thinking about cleaning solutions for our electrodes.
Thank you very much, Michelle. That was awesome. I've always enjoyed attending these webinars, and being able to host and attend simultaneously has been an absolute pleasure. As a thank you for all of you that have come out today, I'd like to offer you a discount for all the services that we offer in terms of classes. So I offer HACCP classes through the International HACCP Alliance. We can do that on-site or remotely through GoToTraining. Or there's ServSafe. A lot of the business that we deal with is not only based in wholesale, but in retail and food service as well. So we offer ServSafe classes and ServSafe certification, which many states require that in terms of food service managers. Again, thank you all for coming out. If we don't have any further questions, we will go ahead and wrap this up. Be sure to look out for the email of the PDF file of this and also the audio.
Perfect. Great. Thank you guys so much. It was a pleasure.